So, let us move on, talk more about what we have seen in the last slide. In regime 1, flames are coming out of the vent. Burning takes place both inside and outside. Regime 1 here. Why? Because there is some oxygen which is coming in, so something is burning inside, but fuel rich gases go out which are hotter, so they auto ignite when they are mixed with some oxygen outside the compartment also. That is regime 1. Correct. Basically, we are talking about the fully developed fires. Now, this indicates that the quantity of air available inside the compartment is not sufficient. Oxygen is going to limit the burning rate. Now, again in the regime 1, the burning rate is almost independent of the amount of fuel and its surface area, and only proportional to the amount of air supply. Obviously, see, fuel air mixing, because of dissolved diffusion flame, fuel air mixing is very critical. If one of the commodity is going to be affected, then the burning rate will be affected. Now, the mass burning rate, or when the mass burning rate increases, heat release rate also increases, maximum temperature also increases. So, when I say mass burning rate, I can connect it to the severity. So, thus mass burning rate increases linearly with ventilation factor. Here, from this point, linearly with the ventilation factor, and until it reaches the value of 12. So, here until it reaches the value of 12, the left hand side, the regime 1. So, you can see that this can be considered as linear because of the spread in the data. Now, in the regime 2, burning is dependent on the quantity of fuel, because the ventilation area decreases. Here, you can see that the ventilation factor has the area of opening in the bottom. So, as we increase the ventilation factor, the ventilation area, the vent area decreases. So, you can see that due to that, the burning is dependent on the quantity of fuel present. When large quantity of fuel is present, then we have the regime 1 where the fuel can come out and burn. Basically, we are discussing about the regime 1 here. So, due to severity of the compartment fire, we can say that when the mass burning rate is exceeding a particular value, the fire becomes more and more severe. Duration also will be correspondingly dependent on the fuel load. So, what we can say in summary is the duration and severity of a compartment fire are dependent on which regime we are working on. That is, again we can say in summary, the ventilation conditions affect the duration and severity. So, let us do some small analysis about the smoke movement in developing fire. So, let us consider an enclosure which has some length, then it has some width and some height. So, height is the ceiling height. For example, this is the bottom floor and this is ceiling, and there is a fire source of some area, and mass of fuel coming out of this fire source, and we can see that there is a flame which is there. Now, the smoke layer is established after a particular height. Here, the smoke layer height, for example, HS is the height of the accumulated smoke layer measured from the bottom. So, we will go back here to just give you a picture in this. So, this is the smoke layer, this is descended to some height. So, this height is the smoke layer height measured from the bottom. So, here in this time 261 I have shown this. So, that is there. So, total height of the compartment is H. So, the height above the measured smoke, or bottom layer of the smoke layer, you can say bottom layer of the smoke layer will be H minus Hs. So these are the nomenclature. We have control volumes we can define. A control volume in the smoke layer, control volume within the plume or the fire, control volume away from that, that is adjacent to that. Now let us see the considerations. Okay, the control volume 1, we can see that hot smoke is accumulated in the CV1. So what is the mass conservation of the, let us do the mass conservation of the CV1. Mass flow rate of the air which is entrained plus the mass coming out of the fuel source will be equal to rate of change. This is actually what? Mass flow rate of the products. Okay, that will be equal to rate of change of mass of the smoke layer. This MCV1 is the mass of the smoke layer with time. Rate of change of mass of the smoke layer with time. M products or mass of the mass flow rate of the air plus mass flow rate of the fuel. Now the mass in the CV1 will have the product mass, which is actually going to say increase as time propagates because of accumulation. Nothing is going out, or if something goes out, it may reach a value. It may actually decrease basically. Okay, as the smoke goes out. Okay, anyway, that also can be accommodated here. But in this, we are talking about accumulation. So now, generally, the mass lost by the solid fuel or any condensed fuel or the mass flow rate of fuel will be much lesser than the mass of the air which is entrained. So I can say I can neglect the mass flow rate of the fuel. Now what is the mass flow rate of the air? So the mass of air entrainment can be got from the Zukowski correlation, which we have seen in the last module, which is some empirical constant into again some ambient conditions, then the heat flow rate. This is convective heat flow rate which is actually 60 to 80% of the total heat release rate Q dot. Then Hs, the height of the smoke layer, which is actually going to be a function of time to the power of 5 by 3. That's it. The empirical constant, some number we can say from the experiments, we can put some number, say 0.21, considering the fire located at the center of the room. Okay, now considering this, now we say the mass of the smoke in the control volume will be what? Equal to density of the smoke, rho S into L into W. L into W, that is the area, cross section area, into H minus Hs. So H is constant, but Hs will vary as the smoke rate descends. Okay, the variation of MCV1, that is the mass of the smoke, is due to the descending of the smoke layer, that is the variation of the Hs with time. Okay, that is, in this case what happens is the bottom initially at when the smoke layer accumulates at the top and comes down, you will see the variation in the Hs that can be substituted here. The density of the smoke is calculated from ideal gas law, assuming constant pressure in the control volumes 1 and 2. Here control volume 1 and control volume 2 here. Considering these two, I can say that rho S Ts will be equal to rho A Ta. So that rho S can be found as rho A Ta divided by Ts, the temperature of smoke rate, but understand that the temperature will also be dependent on time. Initially it will be lower, then it will with time it can increase. The temperature Ts, the smoke layer temperature will increase. That's it. So combining all this, we can write the mass conservation in the CV1 as m dmCV1 by dt equal to rho s, that is rho a Ta by Ts into LW area, L into W into d by dt of H minus HST. Correct. So in the MCV, the only variable which we include in the time derivative is H minus Hs. That's it. Now that will be equal to m dot A plus m dot F is neglected here. So we are only putting m dot A here, and m dot A I know from the Zukowski correlation. So now you see that this is the equation I get for the conservation of mass in CV1. Okay, now assuming that the total convective heat from the fire is delivered to the smoke. Okay, see, when the smoke, there is a fire and there is a plume. So this plume carries some convective heat. So as I told you, the fire generates some heat, say Q dot, heat release rate, which is mass loss rate into delta Hc of the fuel. Now some part of this is given to the fuel itself. This is fuel. Some part of the heat is given to the fuel, some part is radiated out, and some part is convected with the hot gases. This is what we are talking about, Q dot C. Correct. Now, but this Q dot C also can lose heat, so that the smoke layer which is accumulated after this can have a lesser heat transfer. But what we assume here is the total convective, all the Q dot C is only given to the smoke. There is no loss of heat occurs from the plume layer to the surroundings, and everything is transferred to the smoke layer only. So in that case, I don't need to put any fraction for this. Now I write the Q dot C at a function of time is m dot A. Actually, this should be m dot P, products, equal to m dot F plus m dot A. Now, since I have neglected the mass rate of fuel, I can say m dot A into Cp. Some average value of Cp I can take into the temperature of the smoke layer at a particular time minus the air temperature or ambient temperature. That will be equal to, that I can equate to this. Do you understand? So this is the energy balance in CV. What is this? Again, mass entrainment rate is given by this into Cp. This is m dot A, Zukowski correlation, into Cp into this. That will be equal to this. So this is the energy conservation. Okay, so this is m dot A. Nice. Now there are two variables. One is the height of the smoke layer, that is bottom of the smoke layer measured from the floor. Then the temperature of the smoke layer, which can be solved by using these two equations, mass conservation and energy conservation. Basically, I numerically solve this, but I need to know what is the convective heat flow rate. Q dot C should be known for me, but Q dot C is a function of Q dot, correct, and Q dot is a function of T. So that means Q dot C also is a function of T. Now we can do some thing like some approximation based upon how the fire growth. For steady fire, no problem, Q dot itself is constant, so Q dot C will be a constant. For unsteady fire, we can say that the Q dot C will be alpha, some constant depend on materials. Into T power n, that is it. So, let us see this. How we get this convective heat flow rate alpha into T power n. Okay, now let us consider different types of fuels. Corrugated cardboard bundles, then thin plywoods, methanol pool, etc. It is categorized as ultra fast. The heat release rate is categorized as ultra fast. That is, the heat release rate versus time from a ignition point where the sustained flame has formed over the material will be like this. So, ultra fast. Alpha basically is about 0.188. As I told you, this is based upon material properties. We have already seen this. Mass loss rate, flux, flame spread rate, delta H, everything contributes to this alpha. Once the fuel is known, I know alpha value. Approximately for these cases, the alpha value will be around this 0.2 value. Now, the heat release rate with time is very rapid. So, I say ultra fast. Then take this wood pellets, etc. The alpha value will be about 0.05. This is categorized as fast. The heat release rate goes. So, it is non-linear variation because Q dot C will be equal to alpha times T power n. Usually, people have found that n is close to 2 and alpha depends on material properties. So, now if you take say mail bags, that is some bag which is having lot of letters, then some mattress which has cotton and polyester, etc. Some furnitures, then alpha is about 0.01 or 0.015 where you have the medium growth rate for the fire. Finally, a full solid wood cabinet, etc. You will see that again, sorry, this mattress comes in the slow regime where one order less alpha value is seen, so that it is very slow growth. You will not even see the non-linear variation here. So, from this we can easily see that the heat release rate can be, the convective heat release rate can be calculated as a function of the material property which is called alpha and T power 2, that is all. So, you know, if it is transient heat release rate, QC at a particular time can be got from this expression where I substitute 2 for n and alpha can be calculated by the flammability tests. That is the criteria used here. So, now once I know QC, I can substitute here, okay, and I can get the equation and this equation together solved to get the values of Hs and Ts as a function of time. So, this is the way we find this. So, now this is one part where the smoke, the first what we have seen here, the smoke as it descends, how the temperature and height varies, that is dependent on heat release, correct. So, that we have seen first, and the mass entrainment rate of the air. As we have already discussed that the smoke layer dynamics depends upon the entrainment rate of the air as well as the smoke movement is depend on the entrainment rate of the air and the heat release in the fire. These are the things. Now, let us talk about a compartment where there is inflow and outflow of gases. So, let us consider fully developed fire stage in this. Fully developed fire stage. What happens is there is a fire source somewhere and there is a plume which is over the fire and it goes and hits the ceiling and ceiling jet forms. That is, the smoke goes and hits the ceiling and forms a ceiling jet, and we can see that the ceiling jet basically comes. Now, let us say there is a opening, what we have shown here, there is an opening of certain height h naught. The height of the opening is given as h naught. Then you can see that there is a fire in this region which is sustained by the mass entrainment rate of air m dot a, which is coming in, where Va is the velocity of the air which is coming in, temperature. So, you can see this, for this fire to sustain, you have some mass flow rate of oxygen coming in, and the hot gases go to this control volume, and the temperature of the hot gas is Tg, and density of the hot gases is rho g. Then, since this is open, the hot gas goes out of the enclosure or the compartment with a mass flow rate of m dot g. Mass flow rate of the outgoing gases is m dot g, and the velocity, corresponding velocity with which it goes out, is the Vg. Now, this automatically happens in fully developed fire. Fully developed fire, what happens is, first the smoke goes and heats the compartment, the ceiling jet forms, and slowly it accumulates and come down. First, you can see that the hot gas will only go out. There will be no entrainment because the oxygen will be available, that is going to burn this fire. After some time, what happens is, after the smoke layer descends to some height, so out of the total H0, it descends to some height, then there will be some air entrainment from the ambient also going into the compartment, and this now steadily forms. So, there will be a height, okay, where above which the hot gases goes out. There will be no entrainment of air. But below this height, I will only have entrainment of hot gas. That means the smoke layer will transient. That is, the smoke layer forms, slowly descends down. Okay, now once it sees the enclosure also, it descends down to some extent. Enclosure opening of say some height, it descends down to some extent, then it goes out. After that, the smoke layer doesn't descend. The smoke layer height will not change after that particular time until the steady burning occurs in the fully developed stage. So, this height, what I call as ZU, will be the height from the top or the ceiling at which a neutral plane forms. This neutral plane will be like a boundary layer. It is not a fixed plane, it is a virtual plane, where above this neutral plane we will see only outgoing gases. Below the neutral plane, you will see the entrainment of air coming into the compartment. So, Hn from the bottom, measured from the bottom or floor, is the neutral plane location where delta P is 0. Okay, now delta P is 0 here. Nothing happens. So, nothing comes in or goes out at exactly the neutral plane. Above the neutral plane, when you say delta P, I say delta P between the compartment and the outside, that is positive, so that the gases go out. Below the neutral plane, delta P, which is again P of the compartment minus P of the air, that is negative, so that air comes in. Do you understand? So, above the neutral plane, delta P is positive, below the neutral plane, delta P is negative. So, I say delta Pu, that is the delta pressure drop or pressure difference above the neutral plane, which is actually going to drive the hot gases out of the compartment, and below the neutral plane, you can see that the delta PL is actually going to drive the air from the ambient towards the compartment. Now, here you can see this graph, this difference is delta Pu. What is this difference? This is the compartment pressure, okay. So, this is the air pressure and this is the compartment pressure. So, P in the compartment and this is P in the ambient. So, P in the compartment is more than P in the ambient, so the flow goes out. In this case, this is P in the ambient and this is the P in the compartment. So, you can see that here P in the compartment is lesser than P in the ambient, so that the ambient gas air comes in. So, this is the scenario I get, which is automatically established in a opening of a compartment, where in the top part of the opening the hot gas blows out, and in the bottom part of the opening the air comes in, where this is separated by a virtual neutral plane.